Здравствуйте. Hello.
Hello.
Sorry for being late.
Здравствуйте.
Sorry for getting late. Извините, что опоздал. Я просто был на занятиях, и пока пришел сюда, время прошло. И, Саша,
Да.
мы кого-нибудь еще ждем? Просто не знаю.
Я думаю, что там студенты появятся. Я не знаю, китайцы дизайн жунку подойдут или нет.
Я не знаю, они что-то еще не пишут давно. Как себя чувствуешь, кстати?
Ну, я вроде выздоровел более-менее. Но зато у меня все остальные заболели.
У меня брат заболел. Я, правда, с ним
Что?
не общался. У меня брат, говорю, заболел.
М.
39 температура.
Ну вот да. У меня какой-то еще остаточный кашель остался.
Я
Я
чувствую, тут
обычно всех заразил, так сказать,
пол
своим.
Москвы. У меня, правда, дома болеет, но не с такой температурой. Я там
Ну да, эта зараза, она активно сейчас распространяется дальше. Это правда.
Okay, we're waiting for another couple of minutes and then we begin, okay?
Yes. Сейчас тут Павел подойдет, он немножко опаздывает. Ну, на Джунху я не знаю, может, подойдет он или нет.
Я, кстати, буду делать доклад на семинаре в Долгопрудном в эту пятницу. У них там, видимо, у Бондова какая-то освободилось место, меня пригласили заткнуть дырку. Вот.
Мгм. Ну, хорошо.
Да, нормально. Посмотрю на Бондова, а то его там не видел, если он там будет.
Да.
Интересно, что вроде Коняеву дали визу в Австралию.
Да?
Да, это я думаю, что
Это
просто
Молеву,
так.
что ли?
Не, там у них какая-то конференция эти
Мгм.
новомодной геометрии. Я думаю, там Болсинов с остальными постарались, что всем дали. Ладно, это не важно. Какая-то какая разница.
Ты
Ладно.
его видел, что ли, тут на днях?
Да, даже не столько его, сколько Димаша. Димаш мне об этом расхвастался, что он тоже.
Димаш туда тоже едет.
Да, конечно. Он же главный специалист. Окей. Okay, I think it's time for us to start the lecture. Well, whoever wants to join us, let him do it later. So Yasushi, please share your screen. Today, our speaker is Yasushi Ikeda from Moscow State University, and he's going to talk about the argument shift method in the universal enveloping algebra of GLD, and in particular about the second quasi-derivative formulas for the second quasi-derivatives in this case. That's quite a non-trivial algebraic construction, so please begin.
Yes.
Yeah, please begin.
Thank you. Thank you for introduction. Throughout this talk, we restrict our attention to the algebra particular. general linear Lie algebra. And then there is a so-called symmetric algebra. And we fix a generator of this Lie algebra. Eij, where ij equal 1 to d. And this Lie algebra is isomorphic to Lie algebra of consists of d by d matrices. And in my notation, Eij corresponds to large Eij of this matrix Lie algebra. And this is, in my notation, Ji component is 1 and the other components are 0. So this is Ji matrix unit. Then symmetric algebra is isomorphic to polynomial algebra with d square d square but in d square variable, d square numbers of variable. Then next I'll explain Lie-Poisson bracket on this symmetric algebra. So there is unique or something strange.
What's the matter?
Just I can't write, so
Oh, some technical issues. Okay,
yeah, I'm sorry.
Don't worry. We'll wait.
I think now it yes, now it's fine. There exists unique Poisson bracket on this symmetric algebra, which extend Lie bracket. Again, I'm sorry. Lie bracket. Unique in the sense that this Poisson bracket, which I denote by curly bracket, extend the Lie bracket of the the algebra G sub GT. And this unique Poisson algebra, this unique Poisson bracket is called the Lie-Poisson bracket. Poisson bracket. And then next, since this symmetric algebra is the elements of this symmetric algebra is a polynomial of variables Eij. So we can define a partial derivative acting on this symmetric algebra, which I denote d bar ij, and I define it as a partial derivative with respect to variable e j I. Then these partial derivatives act on this basis element as Kronecker delta, and the rule is like this. And then next, we take dual basis Fij ij of dual space of this generally algebra. Dual basis of Eij. This means that Fij EKL equal Kronecker delta IL del KJ. Then if we take an element Xi from the dual space, which can be written as a linear combination of this dual basis, then we define d bar Xi as linear combination of these partial derivatives, which can also be written like trace of Xi times d bar. Then next, I want to introduce a generating matrix. So now Eij is a basis of GD, and this is a subspace of on the one hand, this is a subspace of symmetric algebra, and on the other hand, this is also subspace of the universal enveloping algebra of the algebra. And
Sorry, we don't
Oh,
hear
yeah.
you.
Yes. Just I'm. Then I write I write small e for the matrix as composed by Eij, like E1D, E1, E D D. And if we consider these entries as elements of universal enveloping algebra, then we can consider this matrix of the element of this matrix algebra, and or if we consider these entries as elements of symmetric algebra, then we can consider as this matrix algebra. So this is isomorphic to, for example, universal algebra and matrix algebra. So in the notation of using tensor product, then I can write like E I J tensor E I J. Then yeah. Sorry. So my hand is kind of dry, so I can't use tablet very well. So sometimes.
Don't worry. This
Yeah.
happens. Yeah, just take your time. I think we're not in a hurry.
Yeah, thank you. So then I will write C as center of universal enveloping algebra, and C bar is a Poisson center of symmetric algebra. Then fact is that we can consider trace of E, trace of E square, and so on. And these are as I explained, can be considered as an element of universal algebra or symmetric algebra. In both cases, these belong to center. And the first D element the first D elements are free generators of these centers. Freely generate C or C bar. That means V is isomorphic to polynomial algebras of the element and the correspondence under this isomorphism is trace EI corresponds to the ice variable. Similarly, it's also isomorphic to C bar in the same manner. Yes. Then next.
I just would like to make a remark that
Yes.
this isomorphism is actually this just isomorphism of two free algebras. So whenever you have a set of generators, you can identify the free algebras in one set of generators with the free algebra in the other set of generators. However, it turns out that there exists an abstract map from universal enveloping algebra, from the symmetric algebra to universal enveloping algebra, which gives you an isomorphism on the level of algebras, or on the level of centers. That's so-called Duflo map. And it is really interesting that how this map is related to the construction Yasushi is going to talk about today. We don't know how it is related. Maybe somebody can tell us later. Okay, sorry for interrupting you.
No. The flow map is generally what kind of map?
It's a long story. We'll talk about this later. The flow map is just a map from from symmetric algebra to the universal enveloping algebra, which is kind of combination of symmetrization map and certain differential operator on symmetric algebra. And the fact that it induces isomorphism on the level of centers is quite a non-trivial fact.
But it isn't isomorphism algebra from
it is not the isomorphism of algebras on the level of algebra of universal enveloping algebra, just because universal enveloping is not commutative, whereas
symmetric
commutative. So it cannot be, but it can actually, when we stick it to centers and even to some larger algebras in general, it can still give you a commutative subalgebra. So it can still give you an isomorphism. Okay, we can talk later.
Then classical theorem on which my today's talk based is proven by Mishchenko and Fomenko ごめんか。In 1978 is the following. For arbitrary Xi from the dual space, and for arbitrary remark is that this theorem is this theorem is true for any real algebra and moreover more general a Poisson manifold setting. But in my talk, we only need this kind of form. And for arbitrary Poisson central element, and for arbitrary non-negative integer, dxc, m's power of dxc of x and n's power of dxc y are Poisson commutative. So we can define argument shift subalgebra. Algebra.
What is GD here in theorem 1?
GD is just a general linear algebra. GLDC.
I think in this case, the theorem is still valid for any Lie algebra.
Yes.
You just need to modify the definition of dxi, but otherwise it is just general statement, a general fact about the algebras.
Yes. So we can define a commutative subalgebra CXC bar, which is generated by the Poisson center, and I'm sorry, probably I use notation DXC bar, so more precisely I should write DXC bar x DXC bar square x and so on, and x is a Poisson central element. So we can define commutative subalgebra generated by C bar dxi C bar and dxi square C bar and so on. And this is commutative. So next Next, I want to talk about quantum argument shift subalgebra. In my talk, the word quantum means in universal enveloping algebra, because the deformation quantization point of view, universal enveloping algebra can be regarded as a kind of deformation quantization of corresponding symmetric algebra. So quantum means that it is an object in the universal enveloping algebra corresponding to the classical element in the symmetric algebra. Then the first problem proposed by Wimberg in 1991 is Wimberg 1991 is Wimberg proposed a problem like the following. So is there a corresponding commutative subalgebra in the universal enveloping algebra such that the graded algebra associated to this commutative subalgebra is the argument shift subalgebra in the classical sense. He proposed this problem in 1991, and many people studied this problem, and the answer is known yes. And moreover, such C6C is unique.
Probably it's necessary to specify that here is what does it mean, the commutative subalgebra corresponding to sub psi. It actually means that when it is well known fact that if you take the graded algebra associated to universal enveloping algebra with respect to standard filtration, it is isomorphic to then this graded algebra is canonically isomorphic to the symmetric algebra. And C psi can be also, when we restrict this isomorphism to C psi, then it is the question that we should obtain actually C bar psi. You see? They take the graded algebra associated with C psi, then it should be isomorphic to C box I. That's more or less it. Oh.
And this answer is given by, for example, by these people like Nazarov, Roshansky, Tarasov, Lyubimnikov. Give the answer to this Wimber problem. So and as I already mentioned, we call this unique commutative subalgebra 6 in of the universal embedding algebra. The quantum argument shifter subalgebra. Quantum argument algebra, or it is also called argument shift algebra is also called also Mishenka-Fomenko subalgebra. So this 6 is also called the quantum Mishenka-Fomenko subalgebra. So the second problem we want to the second problem I am Georgiy Sharygin, who is my supervisor, is it also possible to lift this operator defined linear operator on the symmetric algebra to DXC, which is a linear operator on the universal enveloping algebra. And what we figured out is that the answer to this question, this problem is also affirmative. So to explain this this answer, I need to introduce the following operator on universal enveloping algebra. So now I explain it. Then the next definition is given by Gurevich, Pyatov, and Saponov. Gurevich, Pyatov, Saponov in 2012 is the following. The quantum derivations d dij are the matrix elements of the unique linear map D from the universal enveloping algebra to the matrix algebra of universal enveloping algebra. Ex. This is also in the tensor notation. Eijx times Eij. And the condition is of this linear mapping is such that the first condition is in fact first condition and second condition are quite similar or mostly same as the classical component, and the first condition is the scalar is killed by this operator, and the second condition is it act on generator as Kronecker delta. And the only third condition is a bit different from the classical one. And in my talk, I call it as quantum Leibniz rule. And it is for every element d of xy is dx times y plus x times dy. So far, this is just Leibniz rule, but we need additional time in the quantum case. And this is given by the this like this. So and since dx is matrix, so this product is matrix product. Matrix product. And so now I can explain the answer to the problem 2, and And our theorem is that can be formulated like following. And this is the quantum argument system subalgebra formulated, which is formulated already before, is generated by the center of universal American algebra and the here I need to explain the operator Dixie is trace like the classical case trace of C times the operator D, which is now which is defined now. And our result is that the quantum argument algebra is generated by center and the first derivative with respect to this operator, and second derivative, and so on. So then next I want to define just notation is that I write C sub n as subalgebra generated by derivatives up to nth order. So our theorem implies that this increasing sequence of subalgebra, the union of this increasing subalgebra is just quantum argument system algebra. And so from now, next section is my main section, and I'm going to talk about generator of this algebra. And so next section is generator of quantum argument shift algebra. And my notation is that if X is any D by D matrix, then I'm going to write it component like this. And so, and I also write x upper I, like for i's row vector of this matrix. Row vector and x row of j for j's column vector. J's for vector. Then my 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 result about 2 years ago is that the quantum derivative of the matrix elements of the power of this generating matrix small e is given by the following f plus n minus 1 e j e n I plus f minus n e n I j where f plus minus n of x is defined plus minus divided by 2, which are polynomial of over the integer ring. here a bit my notation for example this notation is a kind of confusing because I also write so this notation is the notation for notation introduced just before, and this is this notation means this m means the power. So it's a bit confusing, but I think still we can understand the context. So next. And other fact I should mention is if I write the bold one for the operator defined like x times bold one, where this one means the identity matrix. So this means the matrix in which the diagonal elements are x and other non-diagonal elements are 0. So I introduce this operator. Then I should mention that quantum Leibniz rule, implies that this operator, the bold one plus quantum derivative, preserve in fact the multiplication x. So this operator, the bold one plus quantum derivation, is not only a linear mapping but also a homomorphism of complex algebras. Which is also important fact to calculate quantum derivation for arbitrary central elements of universal mapping algebra. And now and also and I introduce a bit convention which is useful in my talk. Is I use convention for f minus minus 1 of x equal 1 and place e minus 1 equal minus 1. I don't know if probably I don't know if exists the inverse matrix of this generative matrix, and I also think that probably there is no such inverse matrix, but just as convention, I introduce this notation. Then the proposition is that if I write x for the trace En, which belong to the center of the inverse MPN algebra, as I explained in this talk. We have one plus d of this trace x trace e to the power e to the power n can be written minus 1 n trace e n minus 1 e. And the second is modulo the first derivative. Maybe it's better to write in the next slide. So and the second is modulo modulo this subalgebra generated by the center and the first order quantum argument shift. The second quantum argument shift of this central element is given like following. Minus 1 is replace f minus n minus k minus 2 times f minus k e like this. These are a bit complicated formula, but remark is that remark is that thanks to the fact, thanks to yes, thanks to the fact that operator 1 plus d is 1 plus d preserve also preserve also product. We can generalize this proposition, this formula. In an appropriate manner. Or not only single trace, but also finite product of these traces. So we can generalize these formula for arbitrary this kind of element, and since the center of universal enveloping algebra is subalgebra generated by these traces, so in fact we can calculate for example these elements for arbitrary central element X. I don't write the precise formula just because these fully general formula is just contain many indices, and just it is confusing to write, but I have this remark. So based on these observation, rather simple consequences from this proposition is that from the first part of this proposition, we can understand that 6C1 is generated by trace Xi e to the power n over center. And from the second part of this proposition, we can understand that 6C2 is generated over 6C1 by the following element, which I should explain these, which I should introduce some definition just after this, but using appropriate definition, we can write and like this. Soon I explain this symbol. This large T means this is transpose. Transpose. Transpose of A. So next I should explain this notation and yes.
So sorry, C2 here
yes.
means the subspace in the algebra in the quantum argument shift algebra generated by the degree 2 derivatives, right?
Which one?
C2. What does it
Yes,
mean?
yes. C2 is the subalgebra generated by center and the
Derivatives up to degree 2, right?
yes, exactly, yes.
Okay.
Yeah. Yeah. I should explain. Before proceeding, probably it's better to explain. Yeah. This element is trace C E trace E M plus this. This is because why I can say that C2 is generated by these element. It is because since so here's a polynomial in terms of the JT matrix the polynomials of E. And here indices is just symmetric. So on the one hand we have for example if we have a term regarded to the here from here n's to the power n, from here m's to the m's power of E, then we also have the opposite exchanging m and n. We also have these terms with same coefficients. So that's why we understand that 62 is generated by these elements. So next is, so I explain this notation. What is matrix Pn? What is function tau of C? So I introduce these notation. Maybe. Definition 5. The first is definition of P of n. F plus F plus F plus 0 x P of n 1 x up to n minus 1 power. So these are polynomials of x. So the matrix Pn is the matrix of coefficients of these polynomials. In fact, for example, now you see my slides, right?
Yeah.
Yeah. More precisely, for example, Pn is a submatrix. Submatrix of
I don't see where you write. Sorry.
Sorry?
I don't see where you write this.
Which mean?
The last phrase you said that the Pn is submatrix of something, but I don't see.
Yes. Pn is a submatrix of one large semi-infinite matrix defined by this formula.
I mean that n Pn is submatrix of Pn plus 1. This what you mean?
Yes. Yes.
And then you go Pn plus 1, Pn plus 2, and so on.
Yes. Pn is a kind of submatrix of Pn plus 1. So yeah, you are right. So if we have P6 here, P6 here, then the submatrix from the left bottom corner is P5, like this.
So, sorry, we don't see where you write this P6. We don't see your screen. We only see the slides.
Oh, really?
With definition of Pn. Yeah, but we don't see P6 and others.
I see. Yeah. Anyway, the matrix composed of these particular integers is P5, and P6 is 6 by 6 matrix, just larger than this 5 by 5 matrix, and so on. So back to the, and also now 6:30, right?
Yeah, I think you have about 15 minutes yet. So 15 minutes. That's okay. If you conclude, come to conclusions in 15 minutes, that'd be okay. Okay.
And I also need to introduce matrix Pn, Pnm, and this is the first m columns. First m columns are 0, and after that it is followed by matrix Pn. So this is n plus n matrix. Yes. And second is if A is some scalar n by n matrix, then TC A is defined defined by AI J trace Xi E minus 1 Xi E J minus 1. And the third is sigma of A is defined as A11 0 0 A12 plus A21 A22 here 0 and A1 n plus AN1 A2n plus AN2 and ANn. So it is an upper triangular matrix defined like this. Then remark is that since it can be proven with some amount of computation, we can prove that this is symmetric with respect to I and J. So we can exchange I and j in this formula for arbitrary I and j. That means that sigma of A is always equal to txc of A for arbitrary numerical matrix. Using these notation, using this notation and together with some computation txc 0 pn transpose of pn 0 is turned out to be the generators of subalgebra C2. Trace en en plus trace en. So now we are almost coming to the conclusion, and it is that yeah, here we can. So the theorem I found is that for arbitrary m and n, yeah. Sigma 0 p n plus 2n p m d 0 is a linear combination of using binomial coefficients. E m plus k m plus k. Maybe remark is that this is can be written like using this kind of, we can write in this way also. So now the meaning of this formula is the meaning of this formula is now clear, and so the can't move. Yeah. So this matrix have two integer m and n. But in fact, we can put n equals 0. We can, so here this indices and this indices are same. So the point is that this matrix can be written particular types of this matrix is a linear combination of small sets of generators. And also we have so here the difference of these two indices was even, but there is also a formula for that. The difference is odd number, and it is like n plus n plus 1 transpose of Pm 0 can be written like this: k equals 0, n n minus kk p n plus k n plus k plus 1 p n plus k n plus k plus 1. So again this element is sigma 0 p n plus k plus 1 p n like this. So I think now it's clear the meaning of this formula. Similar. It has similar meaning. So using this observation, we can conclude. I can conclude that. So so now I can state the conclusion, which is corollary to this theorem, is that 6C2 is generated by over 6C1 by following elements. P n plus 1 plus p n plus 1 n equal 1, 2, and so on. So now we have here the before knowing this relations, there were two indices, but now we have only two index n. Sorry, one index n. So in this way, we can reduce the number of generators. So this is my conclusion, and the remaining few minutes I want to explain. So briefly the detail of this, the proof of this equation. So now you see my PDF, right?
No,
No,
we
really.
only see the screen where you write.
Okay. Then probably just when I just need to finish my screen sharing
Mm-hmm.
and share screen again.
Share
Define.
another screen with us, right?
Define.
But I think that I mean that I think the most important part of what you said is that you actually gave a very interesting family of commuting elements parameterized by matrices. Because I think it's quite I never seen this set of elements commuting with each other. Of course, it is nice to know that they come from argument shift algebras, but they do not look like anything we have seen in the discussions with Professor Molev. They look slightly similar to his constructions, but they're still different, and it's really interesting, I believe, because whatever constructions Molev and others have, they always start with coefficients of the characteristic polynomials, and these commutative elements of yours, they appear from traces, and that's different. Okay, sorry for interrupting you. You wanted to say something.
No, thank you for your comment. So now you see my PDF right now.
Yeah.
So yeah. So which one? Yeah. Anyway, so you also see my cursor, right?
Yeah.
So this is the formula I explained, and in fact, this formula is equivalent to two conditions, and the first condition is just put m equals 0. So when put m equals 0, then we have this equation, and the first point is just we need to prove this simplified equation, and we also need to prove the second condition, but anyway, the first condition is here. First condition is equivalent to this kind of combinatorial formula. And the second condition is equivalent to where? In fact, the second condition is equivalent to this kind of polynomial equations. So we need to prove the first combinatorial equations, and also we need to prove the formula for this kind of polynomial equations. And I checked. So I found this kind of relations just by many experiments, and I got sure that these formulas are true, but I don't know how to give formal proof these formula. So I use equivalent formula and formula and to use Mathematica. So as my theorem theorem of matrix relations is equivalent to these four conditions.
Mm.
Yeah, I'm sorry. I just lost.
You just yeah, lost
Lost.
connection, it seems. But I think it is more or less, yeah, we were more or less understood that you reduced the formula you were going to prove to some check-in with computer,
Yes, yes, yes.
and then the computer would actually confirm this formula by direct computation, symbolic computations.
Yes, yes, yes. Here is the code of mathematical to verify these equivalent conditions. So now I just I have finished my talk. Thank you very much for your attention.
No, thank you for your talk. It was really interesting. I mean, even though it was pretty technical, I believe that just the fact that you found a very interesting set of commutant elements in universal element algebra, which depends in a quadratic way on size, and which it's not evident how they appear. I mean, in examples we know from other people's work, from say Professor Molev's work and others, they look totally different, and just the fact that your elements also commute makes it much more interesting to pursue this this construction. Okay, are there any other questions or comments?
It's difficult to proceed the last part because it's technical. I mean,
Yeah, very technical.
the proofs
Yeah.
were omitted.
Yeah, the proof is really very technical, but
Yeah.
again, in my opinion, I should stress again that the set of commutant elements you obtain in this way is quite non-trivial. If you try to prove by hand that these elements do commute with each other, it is not easy, because the coefficients that stand in front of these traces with double size, they are essential. You cannot just put in arbitrary coefficients there. It's essential to have these precise coefficients to make the commute. And why these coefficients show up, is there any meaning in them except for their technical, some technical reasons? It's quite an open question, in my opinion, quite an interesting one. And also look at these, phenomenal relations with binomial coefficients. I've never seen them before. I know that binomial coefficients appear in many contexts, but I never seen these kind of relations. They might appear in some, I don't know, in standard algebras, in some other commutative algebras with differential operators, but these relations with binomial coefficients, they're quite interesting.
Oh.
I've never seen them. Okay.
So
Okay,
you
thank
checked all
you.
these formulas by computer mathematica, right?
Sorry?
You have checked all these formulas by computer, right?
Yes. So I didn't give a formal proof, what to say, logical proof for this. I just yeah, you see, like for simplify or simplify something, and just I calculate the left side subtracted by the right side, and just and you just designate some condition, for example, n and m and l are integer, positive integers, and just told mathematical to simplify these expressions. Yeah. And you see output is or zero. So that means that these formulas are the correct one.
Okay.
I really would love to see what kind of differential operators you obtain in this way if you substitute Eij for some representations in n variables. They might look quite interesting. I see. Okay, but in any case, thank you very much again, and I think it is time for us to stop this seminar.
Yeah.
So next time we shall have a talk by Professor Grinevich,
Гриневич.
I believe. And I don't know if we are going to meet. Yeah, we definitely meet on December 19th, but then December 26th is a little bit doubtful. But okay, in any case, I think you just will send announcements. If there is any questions, just let me know. Okay. Okay, thank you, everybody, and see you next time then.
See you.
Thank you. Bye.
Bye.